Okay, shall we start? I think it's time for us to start. And thank you for coming. My name is Bai Guangdong, and I'm a postdoc and research fellow from National University of Singapore. And my research is on the security of protocols, including Authentication Protocol, single sign-on, and some protocols related to trusted computing. So this leads to today's talk. I'm going to look at the authentication protocols and then compromised backup channels. Okay, so as more and more applications are used in our daily life, and a lot of web services are increasingly delivered sooner under applications. Here, I want to show you some example in the social networking. For example, in Facebook, it is reported that the number of mobile users of Facebook has surpassed the numbers of the desktop users. And also on online banking, we can say that the users access their online banking through the applications are increasing. And until it is estimated that until 2012, there may be more than 80% of users access their mobile banking through the mobile applications. And also for the email services, and the red line represents the users that access their email service through the mobile applications. We can say that the numbers are dramatically increasing. So the problem is, can't we just simply reuse the web browsers to access those web services? And we know that there are two options when implement the interface of the web services. The first one is through the native application, and second one is through the web browsers. And either of them have some advantages and disadvantages. For example, if we implement the interface through the native applications, we can have full use of the device and the APIs provided by the operating system. And also, there is less programming limitation. And also, the native application is running faster than the web browser-based application. Okay, and for the web browser-based application, it can, it's like one implementation and multiple use. And also, it can reuse the multiple advanced and well-developed functionalities provided by the browsers. For example, the JS engine and some security mechanisms like same origin policies. And also, it can be developed faster because the developer just need to develop once, and it can run over different web browsers. So the question is why we do not just simply use a web browser. Let's just look at how the reality will answer this question. So in 2013, there are just about 70%, 20% web services are delivered through the web browser, and the number is decreasing. So as this saying that the browser has become a single application swimming in a sea of applications. So in these scenarios, let's look at how the mobile applications will work and what kind of role the mobile applications play in this scenario. So essentially, the mobile application running like the web browser, it first uses some communication protocols to fetch the content from the web server, and then do some content rendering. However, if we look at the multiple vulnerabilities in the web browser, we can understand that this task is a very hard and complicated task. For example, on the content rendering side, there may be some code injection attacks, which means the attacker can somehow inject some malicious code into the content fetched by the web application. And this may lead to some cross-site scripting and some circle injection attacks. And there are a lot of research has followed this side. And for the other side, and the web application will use some communication protocols to fetch content. And if we say this this Android application runs on Android side, there may be some new attack surface, and there may be some new trusted computing base, which means the Android applications must rely on this assumption to make the communication protocols secure. So let's come to the focus of today's talk. We're going to look at how current applications will implement the web authentication protocol and schemes, and we'll look at how this authentication protocols works, and we'll look at how the authenticator, which means some credentials in the authentication protocols, and how this authenticator are managed by the Android application. And as we just mentioned that there may be new attack surface introduced in the Android side. So we'll look at their backup channel, which I believe is a new attack surface for the web authentication protocols. So I basically will introduce how the backup can be dangerous to the web authentication, and we will see how we can abuse these backup channels. And last, I will look at some case study to show the impact of such kind of threat. Okay, so the first part is the web authentication on Android. And you must be very familiar with the web authentication. So an authentication basically is a process by server side to confirm whether a client is who it declared. And this must be one of the most used web services. So how we want to look at how the Android applications will implement the web authentication schemes. And our goal is to learn the approaches that the current or contemporary applications use to implement their authentication schemes. And we will focus on how the authenticators are managed. And we have manually analyzed the top ranked 100 applications from Google Play. And our method basically is reverse engineering and traffic analysis. So this is a short summary on our result. From this top ranked 100 application, we found that there are 66 applications using the authentication scheme, and in them, there are 3 categories of authentication schemes. Basically, I will cover shortly in my talk, and including the basic authentication and single sign-on, and the Android account manager. So for other 34 applications, why don't they use the authentication schemes? Because most of them are standalone applications. For example, the news browser and maps and video players, which do not need the basically the user's account on the server side. Okay, so the first scheme, the basic authentication. So the basic authentication refers to the traditional authentication schemes, which can be subcategorized into 3 kinds. The first one is based on the knowledge. For example, the password-based and some security questions. And we found that 34 applications out of the 40 applications use these password-based schemes. And the second category is ownership-based, which means the authentication server assumes that the client owns some device or something that is special to that client. For example, the SMS, short message-based, and some one-time password-based schemes. And also, there is another category called inherence, which means the authentication is based on some special thing of the client. For example, the fingerprint and even retina patterns. But unfortunately, we didn't find any application use this. However, the system do use this inherence-based authentication. For example, in some new version of Android and new devices, they use the fingerprint to unlock the device. Okay, and I will introduce you that there was some work which tried to investigate the confidentiality of these fingerprints, and that was presented in this year's Black Hat US. So let's do some abstraction, how the basic authentication works. And in the desktop side, the web browser will send some username and password to the web server, and the web server will generate some credentials like session ID, like some credential cookies, and they are planted into the web browser, right? So we call this credentials authenticators, which means they can indicate the client login session. And example including what I mentioned just now, the cookies, session ID, and some OAuth token, OAuth code. So how does the web browser protect this authenticator? They basically use some same origin policy or content security policy or other security mechanisms. However, let's look at how the Android application will do this. So basically, the Android application use some like RESTful API or WebView, which was mentioned by previous speaker. So the Android application uses two interface to send the username and password to server side. And similarly, the server side will generate authenticator. And this authenticator located into the Android side, and it will either put it into the content provider or use some shared preference to store these authenticators. So eventually, these authenticators are located into the internal storage of this application, which located in the data application name, this folder. Okay? So the second scheme is called single sign-on. And also we start from the desktop side. I believe most of you have looked at this, and especially this part, which means you can use like your Facebook ID or your Google ID to log into a third-party website. And we call this a single sign-on. Basically, it's Kerberos like single credential authentication schemes. And there are a lot of major companies have implemented this single sign-on. For example, Browser ID or Facebook and OpenID. So there are three parties in the single sign-on, right? The first is the user. And the user sends its username and password to the identity provider, which we call it IDP, and get some token from IDP. And later, the user presents this token to a third party, which we call it relying party or RP. And this token will allow the user to log into this party. So let's think about what is the single sign-on process on the Android side. The relying party now becomes the application. And if this application wants to use single sign-on services provided by some IDP, it will import SDK released by the IDP. And examples including the Facebook Connect, Twitter ID. So basically it means that this application can log into can allow the user to log in, use their Facebook ID or IDP ID. Right? So here I want to use a concrete example to show this process. And this one is using the Facebook Connect. And we divide it into two parts. The left-hand side part is the scenario that there is no Facebook native app implemented on the device. So what will the SDK do? It will initiate a web view component and do the authentication with the Facebook server. And at this pass, the Facebook server will generate some secret cookie, and later these cookies are used as credential to get some OAuth access token from Facebook server. And for this scenario, both the secret cookies belonging to the Facebook and the OAuth access token belonging to the RP app are located in the internal storage of the RP application. Okay? And the right-hand side scenario shows there is native Facebook app implemented in the Android device. So basically, the RP app will request IDP, namely the Facebook application. So the application will send username and password to the Facebook server and get the cookie and the OAuth access token. And it put the secret cookies into its own internal storage, and then transmit the OAuth access token to the RP application. So you can say that these two kinds of authenticators are located into different places, and you can just keep this in mind, and later I will show you the problem. So the last authentication scheme is called Android Account Manager, and I think most of you have seen this. So which means you can add some accounts into the system. So this account manager is a centralized and delegated authentication service and account manager. So the app developer can only need to implement some interface, then it can delegate the whole authentication process and the authenticator management to the account manager. So let's show how it works. So the developer basically needs to implement two things. The first one is account authenticator, which means, okay, what kind of account you are going to use and what kind of type is the account. And the developer also needs to create an activity through which the user can enter his credentials. So after this, the authenticator will do the account manager will do the authenticator management, and it will load all the authenticator into a database located in this folder, which belongs to the system. And later I will show you this. So if we think about the protocol security, we probably have three layers. The first layer is on a design level, so which means some protocols can be designed for example, miss some nonce, which lead to replay attack, or miss some signature, which lead to man-in-the-middle attack. So basically, we have some tool-like provider flag pair to detect such kind of design level problem. And the second level is implementation level. So the basic idea is even the protocol designed secure, the implementation can introduce some bugs, right? For example, in this case, and not all of the messages are covered by the signature, which provides a chance to the attacker to do a man-in-the-middle attack. And also, some authenticators can be implemented guessable by the attacker. Okay, so these are two traditional layers that researchers most think about. And here, we want to remind that we probably need to think about the infrastructure level, because the code, the implementation of the protocols eventually rely on some software stacks to work. So what if this software stack are compromised? Right? So there is some previous study to look at the password leakage through the compromised ADB channel, and this work was presented in HitCon last year. Okay, so let's keep in mind the infrastructure level security, and we review the 3 kinds of authentication schemes. In the basic authentication, the authenticator eventually located into the internal storage of the app, right? And also in a single sign-on case, the authenticators are also located in the internal storage of the apps. So let's look at this. This is the internal storage located in the data folder. And we can say the owner of this is the user ID of the application. And we look at the account manager. The authenticator are located in this data system user 0. And the owner of this folder is the system. So let's look at how it will be different of this kind of authenticator management. So before that, I would recall the isolation mechanism of Android, which was introduced by a previous speaker. So we know that each application runs in an isolated sandbox, which means that each application can only access its internal storage, and even some application is compromised, it will not get access to the internal storage, right? But the problem is there may be some, okay, I will just skip this, which means we do some abstraction. Is the application usually simply located the authenticator into its internal storage, right? So we want to ask, what if this kind of sandbox is bypassed? Do you think there is any chance? Yes, there is. If we think about the backup functionality, which is quite useful functionality, right? So the backup functionality is basically works like this. We have some backup application which wants to back up the data belong to another application. So essentially, this sandbox must be violated, right? So the second part is how do we implement this backup in Android side? And there are 2 ways of backup on Android. The first one is called a root-based backup, which means after rooting the device, the backup application can be granted the root privilege. Then it will naturally have access to any other application's internal storage, right? And the second one is called ADB Based Backup. Let's look at this ADB Based Backup. So I believe all of you know this ADB, right? It's basically a debugger bridge. So a special thing I want to remind you is that the ADB runs on a higher privilege than the traditional application, than the normal application. Although it's lower than root, but it can have some privilege that the normal application does not have. So how does this ADB-based backup work? And let's think about, we have Android device, and the backup app runs on a user level privilege. So how do we implement the backup? We simply connect the Android device to the PC and run some command, ADB share, and run a command called app process to start a process on Android side. And this one will get the privilege of the ADB. So basically, it runs on a system level or signature level, right? Then it will have the privilege to do the backup. And then the backup application only needs to invoke this proxy to do the backup. Okay, so a little detail. The proxy will use this command bu1 backup, and which will generate some backup data, which is a format of .ab. And let's look at this. So basically, it has a magic Android backup, and it has some version, and also it specifies some encryption algorithm. And by default, this can be none, which means ADB, the backup data will not be encrypted. Okay, so this is how this command works. So once this one is executed, there will be some interface prompt to the user, and then user can choose to back up my app. All right? So let's think about how this backup channel can be a threat to the authentication protocol. The first one, if the backup application locates the authenticator belong to the victim application to some globally readable storage, then the malicious app can just read that one to get the authenticator. And the second, if the ADB proxy is not accessed, is not controlled or protected, some malicious app can also invoke the proxy to do the backup and get the authenticator, right? And we call first case a backup data leakage, and the second case a backup capability leakage. So we have summarized all the backup applications on the Google Play, and so we found that there are about 5 applications, and 4 are root-based, and we found that all of the applications locate the backup data into the SD card. And also there is another ADB-based application called Helium, which also locate the backup data to SD card, and also it has some interface that compromised, which I'm going to introduce in next slide. So this ADB-based backup is called Helium, and it is reported as one of the best applications in 2013. And its developer is the developer of CyanogenMod, which I believe you know this. And they have already released 19 applications on Google Play and accumulate 15 million installs. So I use this to show that even some advanced developer can also make some mistakes, which lead to the capability leakage. Okay, so let's look at how this Helium works. And we basically do some reverse engineering to review the internals of Helium. And in Helium, the ADB proxy is called shell runner. So once the user starts this shell runner from the PC, it will use a command called am start service, which basically will send an intent to the system to initiate to start the main app of Helium. At this stage, it also sends a one-time password to the Helium. So the Helium will locate this one-time password to its internal storage, and then this shell runner creates a local socket server. And if the main app of Helium wants to do the backup, it will access this interface and use the one-time password as a credential. So you think about there's a socket server listed there, and there's a client, and the client requests the server to do the backup and use the one-time password as a credential, right? So Helium allows 2 kinds of interface. The first one is user can use the main activity to do the backup, and the module is called a local backup, and the backup data is located in the SD card. And besides this, Helium also creates a HTTP server. So the user can access this HTTP server from his PC and request Helium to do the backup. So you get this. And we have some protected proxy, which is protected by the one-time password. And the main app of the Helium will send this password as a credential to invoke the proxy. So basically, it works in this way. Okay, so I will show a little of the code to show how this works. And initially, the proxy is start. And then it will create a local socket, server socket. And then it generates a UUID. You can think it as a completely random number. And this UUID is used as the credential. So how this one-time password is transmitted to the main app of Helium? Basically, it will call this function called broadcast password. And let's look at how this broadcast password works. It will use a command called am-service and use a parameter of the one-time password. So basically, this one will generate an intent and send this intent to share proxy service, which is the main app Helium. Right? So far, the one-time password is transmitted to the main app of Helium. And we can find a logic flaw here if we look at this loop. So after transmitting the one-time password to the main app of Helium, the proxy will listen on the socket server for the request. So let's see how this handle socket works. Basically, it's a finite loop. So it just gets requests from main app and check whether the one-time password is the correct one. If yes, it will serve the request. Otherwise, it will generate an exception. So let's look at this path. If the one-time password is wrong, it will serve exception. So it will call this one, and the execution will exit this function, right? So let's look at what will happen. It will enter the broadcast password again. At this point, think about if the Helium app is uninstalled by the user, and somehow the attacker installed an app which has the same name of the Helium. What will happen? The proxy will enter this again, right? And execute this command again. So basically, the one-time password was sent to the malicious app. Right? I hope you get an idea. So this is a concrete attack process. And we can do some evaluation on this attack. Basically, it is not that easy because it requires the Helium uninstalled by the user. And also the attacker needs to install a malicious application which have the same name as a Helium. So the advantage for the attacker is that once obtained a one-time password, it can do the backup at any time because it just needs to use this one-time password as a credential to request the proxy. And another problem is Helium does not do any wrapper on the proxy, which means it will directly execute the command that Helium main app sent to it. So basically, the attacker can generate any comments it wants the proxy to run and send to the proxy. And this command will be run on a signature level privilege, right? And another attack is attack the WebBased Backup, which I mentioned before. So the Helium will open a HTTP server and listen on 5,000 port. So basically, any application which has internet permission will have the, is able to invoke this, is able to access this port. Right? So we also reverse engineering and find out the interface. And basically, the malicious app only needs to access this URL and send a HTTP GET request to fetch the list of all installed applications. And then it can send a POST request to do the backup and also do the restore. So basically, we also do the evaluation again. So the attacker, the disadvantage for the attacker is the HTTP server needs to be opened by the user, and by default is closed. And also the application needs an internet permission. However, the advantage for the attacker is that it also can back up the target victim application at any time. And it is easier to implement than the first attack. Okay, and then the third attack is, because the backup data is located in a SD card, so the malicious application can directly access the SD card and get the authenticator. But the disadvantage for the attacker is it can only success once the user does the backup on the target application. And advantage is obviously that it is very easy to implement. Okay, so far I have introduced how we can compromise the web authentication protocols by compromising the backup channels. And the third part, we are going to evaluate how this threat will impact the real world application. So, firstly, let's look at the extent of the ADB backup. And want to note that the application won't not be able to back up by the ADB proxy if it uses the Android account manager for authentication. Because if you remember, the authenticator is located in the systems folder by the account manager. And the second case is if the application sets the Android allow backup to false, then the ADB proxy will fail to back up the application. However, this by default is true. This value is true, and we find that only less than 10% application was specified explicitly into false. So we want to look at how many apps will be subject to this attack. Besides the previous top 101 application, we also randomly choose 10 categories of application from Google Play, and we get 10 apps from each category. So basically, we do this thing. We first back up this application and get the backup data, and then we restore this data into another clean application to see whether we can log into the victim's account. So through this, we found that there are 80 applications will be infected, and there are totally 120 applications which will not be infected, because 83 of them does not use authentication, and 37 of them, among 37 of them, 23 use account manager, which, if you remember, will not be impacted by this attack. And also, we found that there are 14 applications explicitly specify that they do not allow to be backupped, so they will not be subject to this attack. Okay, so I want to show you some case study. This one is attack the Facebook application. So we capture the messages exchanged by the Facebook native application and the Facebook server. And we found that there is a POST request from the Facebook native app to the server, and it sends a username and password to the server, and then the server will reply an access token and two cookies, one called CUser and another called XS. So we investigate them and find that this access token is basically a credential in subsequent requests. For example, the user can use it to post a new post. And the two cookies, CUser and XS, are credentials indicating the user has logged into the Facebook. Okay, so all of them is located in this database and located in data Facebook internal storage, which means if we can get the backup data of the Facebook application, we can post anything, use an access token, and we can log into the victim's account, use CUser and XS. And the second case study is now Facebook single sign-on. So basically, I'd like to review a bit how this Facebook single sign-on works. So basically, the user input is username and password, and the Facebook SDK will send it to Facebook server and get these two cookies, if you still remember these two cookies, and later use them to get OAuth token from Facebook server. So this process is the authentication process. And besides this, Facebook implements authorization, which means later the RP application can use this OAuth token as credential to get some information stored on the Facebook server. So basically, the user has to authorize this process, which we call it authorization. So what will happen if the attacker can get these cookies? And basically, the CUser and XS, which belong to Facebook.com, and the OAuth token are all located in the internal storage of the RP application, right? So the problem is Facebook completely delegates the secrecy of these two cookies to the RP application, which means if the RP application allows these two cookies to be backed up, the attacker can use it to log into the user's Facebook account and do anything he wants. So this can completely violate the authorization, which is the initial intent of this single sign-on. Right? So we tell this to Facebook, and their opinion is they completely trust the RP application because they think that if the RP application is not trustworthy, then it can use phishing attack to get the password. But the problem is if the two cookies are under control of Facebook, it can set the allow backup to false to protect them. But if you delegate this two cookies to the RP application, then if the allow backup is sent to false, it can be subject to our attack. Right? So the last part is how can we mitigate this attack. So basically for the developer of backup application, they should try to build some secure ADB based backup, which means they should prevent basically the backup data and backup privilege from exposing to some malicious application. So they should have some, secure access control mechanism or even formally verified mechanism on the ADB proxy side. And they should think about the secrecy of backup data. And of course, they should manage the life cycle of ADB proxy, which means once the main app of the backup app is uninstalled, the proxy shouldn't be there, right? And for the developers of web applications, they should try to protect their authenticators. For example, if it is not necessary, they should disable this allow backup. And also they should avoid storing some password in the application's internal storage. And then to try to shorten the lifetime of the authenticators. And most importantly, they should try to avoid implementing their own authenticator management. They can just use Android account manager. So the last slides will be some summary and takeaways. Basically, we look at how the compromised backup channels will impact the security of web authentication protocols. So the thing is, once we implement some functionality that will violate the essential protection mechanisms of an operating system, we should think about it, whether it is implemented secure. Because we are actually push the boundary which break the sandbox. For example, in a research in ScreenMilker, so they find basically some apps use the ADB proxy do the screenshot, and the proxy is never controlled, which means any application can invoke the proxy. Okay, and second, when we think about the security of authentication, we should aware of the infrastructure level attacks. Okay, so that's all of this talk. Thank you.